Welcome. In this video I'll introduce the zpinch, which is a device used for compressing plasmas or material to very high temperatures, very high pressures. It's a slightly different cylindrical configuration than the theta pinch looked at in a previous video. So we're going to use this to introduce several ideas to do with force balance in ideal MHD, and things like magnetic tension and magnetic curvature will be useful to try and explain how the system works. So the basic configuration is we have a cylinder of plasma. We have this direction down the cylinder is called Z. We have a radial direction from the middle, from the axis down the center here to the edge, called R, and then this angle round the outside is theta. And now I'm going to imagine a case where we have a cylinder of plasma, and then we put a very large current down the middle. So we put a current down here, so J is just J in the Z direction times unit direction. So J is purely in Z. Let's write that out here. So J is J Z. And now we're going to assume that the system is constant or uniform in theta and uniform in Z. And so this current is only a function of radius. And this is in the unit vector in the Z direction. Okay, so now we can look at the situation and work out, does ideal MHD hold? What kind of solutions do we get? So if you have an ideal MHD force balance, then we have J cross B is equal to gradient of pressure. And the whole point of this is to get the high pressure in the middle. So we have grad P pointing in the minus R direction. So high pressure here, and then low pressure on the outside. So we can work out what the magnetic field is from the current. So assuming we have current of this kind, then the B field is given by Ampere's law. So if we want B, we can use that the curl of B is mu naught times J. And in cylindrical geometry where d by dz and d by d theta is 0, so we assume all theta derivatives and all z derivatives are all 0, because everything is constant in z and constant in theta. And this just leaves one component, so we just have that 1 over the minor radius, so this radius here from the axis, d by dr of r times b theta is mu naught, and then here we have a j in the z direction, for example. So the only component of the magnetic field is in theta, so we have a magnetic field running around the outside of this machine here. It's running in the theta direction. So we run a current down the middle, we get a magnetic field in the theta direction, and then hopefully this will give us a pressure gradient. So we can use basically J cross B. And now we need to work out what this B theta is. So we can just invert this. So B theta is just the integral. So we're integrating R of R times mu naught times J, or mu naught J Z, integrating it in R, and then divide by R like that. And so we can make some assumptions to simplify this. So if we assume, for example, that J, so assume so J Z is constant. It's constant. So that there's no variation in R. Then we have that B theta. This is all just constants, these J mu naughts and JZ, so this just becomes a half R squared. And so this whole thing just becomes a mu naught JZ over 2 times R. And so the magnetic field is just linearly increasing with radius. And so we can put this into the J cross B formula. So this is J Z cross B theta, which is, so we have J Z, and then B theta we take from here. So we have a mu naught, another J Z, so it's squared over 2 times R, and then Z unit vector in Z crossed unit vector in theta, and this is minus unit vector in R. So now we get that there's a force which is in the negative unit direction, so it's in inwards in the cylinder, and it's going to be balanced by a pressure gradient. So we have J cross B is grad P, and since J cross B is only in the radial direction, so grad P must also be in the radial direction. And so this grad P, we can write this is dP by dr times the r in the radial direction. And so this whole equation we just write as jz squared mu naught over 2r. We get a minus sign, because here we have a minus, and that's equal to dP by dr. And so, since this must be positive, dP by dr must be negative, and so pressure is highest in the middle and lowest on the outside. So we have Jz pointing down here. We then have the magnetic field, which is in the positive theta direction. So we have P is in this direction. And this is producing a J cos grad P in this direction. So grad P is in towards the axis of the machine. And so we have highest pressure in the middle, lowest pressure on the outside. So we can work out what the pressure must be. So if you have pressure, some function of radius, we know that at the edge of the plasma, so at R equals A, so we call A is the edge, so edge of plasma, we know that P is equal to, for example, say P equal to 0, so we just arbitrarily choose some external pressure, so we might have a vacuum chamber, for example, so that the pressure is very close to 0. So at the edge of the plasma we have no pressure. To work out what the pressure at any given radius is, we can basically integrate this dP by dr from the edge inwards. So we can go from the edge of the plasma to some location R, and we're going to integrate dP by dr, so this is minus Jz squared mu naught over 2 times R. And so here we just end up with this is, well, these are constants, so Jz mu naught over 2, and so we just end up with we get mu naught over 2 Jz squared over half R squared from A to R, and this gives mu naught Jz squared over 4. So you get half from here, half from there. And then here we have an A squared minus R squared. And so this is just for the case where Jz is uniform. Then we get a profiles that look like this. So we have a plot. So we'll try and get several things on the same axis, so you can see. So this is radius. This is going from the center of the machine outwards. We're looking down the axis of the machine now. So the pressure is a parabolic equation like this. So P goes like this, out to the edge of the machine at location A. The magnetic field strength goes first linearly up. So this is B theta, which is proportional to R in this region. Once you go outside the plasma, then this actually drops. So this becomes proportional to 1 over R outside the plasma. And in this case, we've assumed that plasma current, which I'll draw. So this was Jz here. So we've assumed plasma current is constant, so B increases and pressure is parabolic. So Z pinches have the advantage that the magnetic field is around the machine, is around the plasma, so we don't have the end loss problem that theta pinches have. Unfortunately, as we'll show later, they are unstable, and so as the plasma compresses, it's subject to many different instabilities, and the plasma ends up breaking into small pieces, and so it doesn't confine plasma either. Okay, so that's the solution for a case where we have a uniform current density. We can look at a slightly more general solution where we have a current, and so now we can look again at what this expression is, so in terms of the vector quantities. So we have J cross B, and we have this and there are mu naughts. This is the magnetic field part, so we have d by dr of r b theta. So this is the current producing magnetic fields. This is from Ampere's law, and this is in the z direction. This is the current, and then we're crossing that with the magnetic field b theta in the theta direction. And so at least so far we haven't assumed anything about the form of the current profile. So this is minus 1 over r mu naught from here. So d by dr is over r b theta. B theta, so z cross theta is just minus r. So we have this force in the radial direction. So we can split this into two pieces. So this becomes an r, then a db theta by dr plus b theta. And so this whole expression for j cos b we can write in two components. So we have a expression here where we have this b theta component here, so we have b theta squared. So we have a minus b theta squared. Now we have an r mu naught from that constant there. And then we do the same trick as done a few times before. So this b theta on the outside combines with this b theta on the inside of the derivative. And we just end up with a 1 over mu naught d by dr. And then we have a b theta squared. So this is the magnetic pressure term. This is in the radial direction. And this, of course, is equal to the pressure gradient. This is grad P. So we have dP by dr in the r direction. And so we can combine this radial derivative of the pressure with this radial derivative of magnetic pressure. And so we can write down expression which is just that the radial gradient of the fluid pressure plus the magnetic pressure. However, in cases where we had straight magnetic fields, so in the slab geometry or the theta pinch, this had to be equal to 0, so this total pressure was constant. Now we have an extra term here. We have this b theta squared over r mu naught, and this whole thing is now equal to 0. So this was the fluid pressure, this is the magnetic pressure, and then this term is magnetic tension. And it's a force which is coming from the bending of magnetic fields. Bending magnetic field like this. And in this case we have magnetic field going around the plasma column. So if you have a bending magnetic field you end up with forces which can also help confine the plasma. So essentially this is the magnetic field trying to straighten out. So you get the bending magnetic fields also produces forces. And you have magnetic pressure as before. And so we can actually derive an even more general expression. So this is for any geometry. So we can use that, so we have J, it's 1 over mu naught curl of B. And then we can combine that with J cos B. So this is just 1 over mu naught. We'll just insert this into here. So we have a curl of B cos with B. Then we can use some vector identities, and this is just 1 over mu naught, and then we have a b dot grad B. Then we have a minus gradient of b squared over 2. This is just a vector identity. And so, yeah, this is an exact vector identity of that case. And so here we just write j cos b is 1 over mu naught. Now we have a b dot grad B minus the gradient of b squared over 2 mu naught. And so in general, and so this is now completely general, we haven't assumed anything about the geometry or that it's a Z pinch or anything. This holds in general for ideal MHD. So the gradient of the pressure plus the sort of fluid pressure plus the magnetic pressure, and then minus this term here, so we have a mu naught, so b dot grad B equals 0. And so this term, this is the magnetic tension term. Now it helps think a little bit about what this means. So B dot grad, if you have a curved magnetic field, so B is going like this. B dot grad is if you are walking along this curve. B dot grad is how is that quantity changing. So in this case, it's as you move along B, how is the vector changing? So how is the direction of B changing? And so if you're walking along this curve, the B field is bending to the right, and so the gradient is that way. So this B dot grad B is to the right, because that's how, as you move along B, this is how B is changing. And this is the curvature, or related to the curvature. So if you're in a circular geometry, if you're in a circle, so if you're in a circle of radius r, then B dot grad B is just B squared, so the magnitude of B divided by the radius, and then it's in the minus r direction, so it's in the minus r hat direction. And so this provides an additional pressure. So here this would be negative, and so we have a plus B squared. So this is the tension term that you find in the zpinch. And so in general, for all configurations in ideal MHD, there's a combination of magnetic pressure and magnetic tension which balance the fluid pressure.